closed ones. And what is this open differential and all? They actually, this open differential is something more rugged, and in order to increase the torque, this differential plays a major role. So it is like this. There are the different topologies what the industries are following is again under we're all exploring what can be done in future. Moving with the comparison among the electric vehicles, you can see the electric vehicles based on the kilowatts motor. So you can see 60 to 120 kilowatts, and plug-in hybrid maximum to 120, and full hybrid again it's a minimum kilowatts, and 48 volt mild hybrid is also there, 12 volt micro hybrid. So based on this, it is linked with the saving potential in percentage. So when you talk about here, we have the conversion process also. Mild hybrid means again the conversion come into picture. Then when we talk about full hybrid, plug-in hybrid and electric vehicles, naturally the high voltage power electronics come into picture. We high voltage power electronics, see whatever we learn in the power electronics subject, we talk about the power MOSFET, we talk about the IGBTs and SERs, all those things, those high voltage aspects come into picture, and how we convert that, how the AC to DC is conversion is taking place, how DC to DC again it is converting, what kind of setup can be there in the future, what are the challenges right now our country is facing. So all these things are they're all under research right now. So just I would like to give a comparison of the electric vehicles where this high voltage actually places. So when we talk about electric vehicle, power electronics topology naturally comes into picture. Then this is statistics of where the top selling light duty of the plugged-in hybrid electric vehicles are there across the world. So naturally, the developing countries as well as the developed countries, they are fastly moving into the electric vehicles. Right now, the only concern is the cost. So once the research is into the peak of it, and if the next 10 years, the complete electric setup is established, I think everyone will have an EV there in our home. Moving with the companies in India, just a gist of whatever I'm talking here is the companies where our country is playing, how different motorcycles or bicycles or scooters or rickshaws, whatever it is. And when you talk about the companies in India, there are different incubation centers where we design. For example, I would like to tell you, I think you might have also read at IIT Madras, an alumni, he has developed an e-bike which is called as Spimo. So this e-bike, you can charge for 1 hour and you can run for 50 kilometers with one charge. And there they have implemented swapping technologies also. You can remove the battery and charge outside, and you can just place it, you can just close it with the latch, and you can run that. Again, the battery technology that plays a major role, what the lithium ion batteries, whatever we are using, how it is being done. So everything is under testing phase. I would like to give this an example because out of I think mostly we're all faculty, we can have a research topic also in such area, battery management systems. So if you look at this bicycles and scooters and motorcycles, rickshaws, here I hope that every institute, let it be your institute or my institute, wherever we'll be having the e-rickshaws. So if you closely monitor the e-rickshaws, they are run by the BLDC motors, where just you have only a plug point. There you have only a single phase. That single phase is again you have an AC to DC setup, and you charge a battery. From the battery only you feed the BLDC motor again, which is again a DC to AC setup is required there. So this I think this we have already seen this. Motorcycles, I told it is being hub motors are into picture. And again, this is how the things are just in the process. And fully electric cars, which you're talking about, the electric vehicles, and that is the future. As I have told you, the battery management system plays a major role here. And naturally the buses, even the government setup is also slowly shifting to the So trial run as the Make in India scheme, or we are just moving with the thing of electric vehicle only. So naturally in Indian railways, we know the entire country will be electrified by 2022. So different batteries is what we require. I think for in your previous lectures, almost the lecture started by 22nd for you all. You might have right now you might be very clear with the different battery technologies what you have. So I'm sure that you all agree that you have chosen lithium ion, because I've seen your previous topics also. You have the basic lithium ion technologies, why it is used. So just a gist of the summary of the previous lectures. It's like lead acid. Again, the important advantages: it's cheap and easily available. Naturally, it will have environmental problems. Moreover, the nickel metal hydride also, you have a high energy and power density when compared to the lead acid. And when we talk about the power density, so what is meant by the power density? So power density means that is the amount of power. So it is the amount of power. So or we can call it as the time rate of energy transfer per unit volume. So that is the power density actually. So that is the power density. So naturally we should have a higher power density, but we have its own disadvantage. But when you talk about a lithium ion, yes, it's having a higher energy density and high power density, long service cycle life, everything we have. And we have minimum low recycling values also. Then again, in variants of lithium ion, why we require a different variants of lithium ion? Again, this is under research. So lithium iron phosphate, lithium manganate, cobalt oxide, lithium polymers, and lithium nickel manganese cobalt batteries, and lithium titanate. So these are the most commonly used lithium ion batteries where we talk about. And mostly when we talk about the polymers, lithium polymers, now they are overtaking the industry also. Now comparison. So I have mentioned in my previous slide, I have mentioned few lithium ion variants, and I'm giving you what are the boons and what are the disadvantages of all the variants. So we can find the lithium polymers. Again, it is under the research stage only. They have low energy density and decreased cycle count is there. But when we talk about the lithium polymer, we have strong charge abilities and long cycle of life, and moreover the improved safety. So when we just look into different variants also, we finally fix with the lithium ion batteries only. When we talk about the lithium ion batteries, I hope you might have seen the various, like previous lectures. I have told you, you have a stack actually. The small, they're all small cells. So for example, you have small cells, each placed like this. So naturally, what will happen if small cells are placed like this? Naturally, for I think they are all stacked together. They are all stacked together, and that will be detachable only. I'm talking about the EVs. So EVs, they are all detachable modules. So one over the other, and you have similarly, you have a coolant also here. And also, see, I'm not talking about cell balancing here. Cell balancing is something different. Means when one is discharging, the other is charging, balancing of those, that is different. I'm talking about how the modules are placed here. So almost, for example, the recent EVs, I think mostly most 7,000 cells we have. Just imagine in the battery setup, small batteries, 7,000 batteries we have. So that is possible only with this lithium ion. So that is why everybody talk about lithium ion batteries. So performance comparison of various batteries used in EVs. So that just now I told you why we are opting this lithium ion. It is more simple also. And lithium ion, again, it is having its own cycle life. Now lithium titanate is under research. It is much more higher than that. So these are the performance aspects, performance comparison of various batteries that has been used in the electric vehicles. Then performance comparison of various batteries in EVs. So when we talk about if we talk about BMS, we should know what is the battery we are using. That battery should be with respect to the watt-hour per liter and watt-hour per kg, because in batteries we use distilled waters. So with that concept, when we just take this slide, it should be with respect to the watt-hours per liter and watt-hours per kg. So see, with this diagram we can choose which battery we can opt. So that is what this diagram talks about. So now, battery technology which is used in various EVs. This is about on-road. On-road, what are the things we have right now? So hopefully in 2022, we will have Tesla cars, more different variants we have, and Tesla Model 3 and other Tesla models also into picture. We just need not talk about Tesla alone. There are many other aspects also. Right now, you or me, anybody can connect, anybody can make a drive. We can run a scooter or we can run a car. All you need is to just register it with the government sector and just get the approval of it, and we can run a bike or a car. That's it. We know how an induction motor work. We know how a battery setup will be. We can use it a power electronic device there, because there in complete electric vehicles only inverter is the heart. And also for there the battery management systems communicate with all the other parts. So naturally this inverter plays a major role, which is completely the heart of the system there. So being an electrical engineer, I think the mechanical industry is being overtaken by the electrical industry. Recently, when we talk about some 6 months back, in mechanical industry, there were only mechanical engineers. Now, when you talk about the electric vehicles, there is one person. Even the recruitment is based with electrical engineers also there, because winding of a motor is done only by an electrical engineer there. Or they should know the design of electrical machines there. So design part plays a major role. If you see the hub motor inside, the winding will be there. There will be small magnets. I'm telling you here, there will be small magnets here, which is current. I'm talking about the scooters or the bikes. Small magnets here. So when you here also you have sensors. Here sensors will be there, and there also the coil winding will be there. So here the recruitment process also, now electrical engineers are there, and we have communication engineers also. When we talk about the electric vehicles, the CAN protocols, other power coding, power electronic devices, the coding, we need a communication engineer or a software engineer there. So when we talk about the vehicles, naturally, when we talk about the batteries, the manufacturing, the chemistry of it, we should be more specific, we should talk more about the rated power and the specific power. The rated power, so complete EV, because it is output power. So in electrical terms, we talk about, if it is a lossless system, what is that we talk? We talk input power is equal to output power. So when we talk about battery, we should have an idea that the state of charge, that should be, which is equal to the depth of charge. Means whatever we are charging, that should be with respect to its output. Means completely it should discharge. Means with respect, and it's not equal to, it is with respect to. It's with respect to the depth of charge also. So state of charge as well as the depth of charge comes to a major role, major picture here. So talking in electric terms, the input power should be equal to the output power. Means a lossless system, this is how it will behave. But when you talk about the battery, the state of health is a major criteria. I'm talking about state of health of a battery. So that is what we will look into in the coming in the next 1 hour. We will discuss about the state of charge, the state of health, the depth of charge, and how an electrical engineer has the opportunity in the battery management system. Now, what is lagging right now in the research? Where are the gaps where we can fill the research? So those things we will see in detail. So moving to the other battery technologies. So as I've told you, there are other batteries also, which is a sodium ion battery. There are the type of rechargeable metal ion battery, which is using sodium ions as charge carriers. And naturally, they have their own pros and cons. Second one is the potassium ion battery, which uses potassium ions for charge transfer instead of lithium ions. So it has its own advantages and disadvantages. Naturally, the cell design is simple. Materials and fabrication process is also cheaper, but the disadvantage is about the energy density, power and energy density, which is, see, it should have a good power density. And solid state battery, and again here we talk about the battery technology that uses both solid electrodes and solid electrolytes. Again, the advantages have the higher energy density, it is safe, we have a good tolerance to high temperatures, and allows fast charging also. And the disadvantage is naturally because what happens here, it may break due to mechanical stress, that is really dangerous, and also expensive to make. Naturally, the cost is also playing a major role. So low temperature operation may be a challenging task in case of solid state batteries. Now we are moving into the BMS. So right now, in previous slides, whatever I've told you, I've given you the summary why we need a BMS. I've told you the different motors that is being used also, and why you require BMS there, and also I've told you the battery which is being stacked. Now let me explain in detail what is the battery management system is all about, and what is that. So in few slides, in coming slides, we will look into the introduction of the BMS, their components, the trends in EV batteries, necessity of the battery management systems, the functionalities and features. Battery management, going to the introduction, I told you there are concerns with lithium ion batteries. So here safe operating area is restricted by temperature and lithium ion batteries. And here temperature, if it goes to minus 20 degree, this battery will not work out. And right now we might have read in news also, there is no electricity in US due to a heavy snowfall, and you cannot drive because the cars are being jammed, battery is not operating, it is minus 20 degrees, less than minus 20. So there is a concern with this kind of battery. So your technology should be with respect to the temperatures also, because the temperature should not restrict the operating point. That is a concern here. And also high cost is also there. So your battery is cheap enough if you cannot remember the last time you have replaced it. So that battery should be designed in such a way. And suitable system which is required for battery safety and protection for prolonging the life of the battery is also a concern of this battery management system. I'm talking about the system required for safety and protection of this battery. Safety and protection. Safety and protection. Next comes the BMS, which we're talking about the embedded system here in the complete thing. Here we protect the cells of battery from damage or that will lead to the prolonged life cycle of a battery, and maintaining a battery in a state which can fulfill its functional design requirements also. So, and also informs the application controller how to make the best use of that right now. Means the power limit, the control charger, everything in a single interaction. We can get all that in the embedded system. Now, so BMS components. So just look into the component. So BMS for an electric vehicle, when you look at it, we have the 4 components here. One is the mechanical development, the software development, the hardware development, and the testing aspects. So if you look into each one, so if you first look into the software design, yes, you have the standards. You have some standards with complete thing. What is this software design? The diagnostics with J1939, They're all codes. They're all codes. That is the engine controller code. So we should know about all these things which comes in the package. So one setup means one battery management system should be able to interact with all the components which is there in the vehicle. So that is the idea. How do we do that? But how do we do that? That is why we are here with the discussion here today. How do we do that? We do that with certain engine controller codes, and actually there is something called as UDS. They're all protocols. Actually, they're all unified diagnostic services. Mainly they're called as the automotive protocols. I think you might have heard this in the previous lectures also. They're called as the automotive protocols. Okay. And this automotive protocols will help diagnose the system, and it will communicate with the ECUs. So they're all electronic control unit. It will communicate. So to do what? To control the fault, to reprogram, and whatever is required. All these things, the diagnostic services does all these things. So if you talk about the diagnostics, there are many other things also, which we talk about the engine control codes, and also it is unified. Because why we call it as unified? I'm talking about BMS. See, right now I'm talking about BMS. I'm talking about the various components of the BMS and what is all required where and where. So now when we talk about the BMS, I'm talking about the unified controller. Means it should communicate with all the other standards also. Unified means, see, there are existing standards right now all over the globe, but all together in one thing, you should bring it into the battery management system. That is also your biggest concern. See, for example, there are A, B, C, and D. Each one is of different standard. Bring all together, A, B, C, D together, you bring it, which is called as a unified. I hope you understood right now. So that is called as a unified standard. Then moving into the hardware and EMC design, the mechanical development, and the hazard analysis, the worst case circuit analysis, the value engineering for combining the PCBs, cost reduction in each board. You might know, see, simulation part, and other things also, the safety critical projects. We talk about this ISO 26262. So all these things, they're all the standard protocols where we talk about how the system should be divided, how the system should be designed. All those things are there. So when you talk about this ISO 26262, this is mainly an automotive specific international functional safety standards, mainly for the electrical and electronic systems. So overall the globe, we follow this kind of ISO systems. So mainly this kind of system, software development, hardware development is mainly specified, mainly for the production of the passenger cars, what we are talking about. So here, moving into the next one. So mechanical development, software development, and hardware development. We should move into the next category where we talk about when we talk about the testing aspect. Your testing should be related with your electrical aspects also. So in the previous slides, I have told you about the winding of a coil, how a coil should be wound, how much it should be, the air gap flux, how much it should be, how much it should be there. And when you why that kind of the data is required. So when we let me take a hub motor itself. Okay, in that hub motor, you can see if there will sometimes, if there is a mismatch in the sequence of the rotor rotating, definitely you cannot rotate it. There will be a jerk there. Jerk in the sense you cannot further ride the bike. You have to stop it. Then you have to again kickstart it. You have to produce the enough flux for the stator to rotate, and then you have to ride the bike. So these are certain aspects. So all these things should communicate with the BMS. I hope you got the point. So it is with respect to the complete system analysis. So the independent testing or validation, the verification, the hardware testing part, the test automation system, completely it should be with the entire system. Then moving into the product development concept to the prototype. Here there are CAD modeling, which is the computer aided design. And when we talk about the computer aided engineering, there are different analysis here, and the cooling analysis part. So here each and every aspect, here a mechanical engineer or electrical engineer, they operate all these things here. So it is just not the mechanical aspect. Here we have the electrical people also entering into the EV and the electric vehicle sector. Now I hope the complete testing will be with battery management system. So completely, this is what we require for a battery management system. So summary, we can take that the complete engine controller means we talk about now it is a battery controller only. It is not an internal combustion engine. Now this engine controller codes, now it will be battery management system codes. So that is the place where you can see how a battery is dominating the sector right now. The only drawback right now in our country is we don't have the charging stations. Once if it is there into the existence, I think the things will completely change. Now moving to the trends in batteries. So I have already given you an example of the PIMO, which is being developed by IIT Madras. So you can see there the battery swapping technique is being carried out. I told you, right? You can take the battery and the battery swapping is also possible. There you can take this battery, means the discharged batteries are replaced by either fully or partially charged one within few minutes. This is meant by battery swapping technique. Again, I'm telling you what is meant by a battery swapping techniques. So this is this means a discharged battery, they are replaced by either a fully or partially charged ones within few minutes. That is called as a battery swapping technique. And there, that is what they do in the PIMO e-bikes also. You can see, but this can be tried out for an extended range also. There the power output is a very simple one, but the research is still there. And the final of during the conclusion, I'll tell you where a power electronic engineer can work out, where we still lag, where in the research we still lag. Now since the trend is there in EV, where we can focus our research, where our papers get published. So I'll tell you that area also. So India market for EV batteries, which is worth billions, okay, $1 billion, and that is between 17 to 30. So mostly lithium battery packs are expected to fall. Definitely the charge will come down, and we can try this battery swapping techniques also with different techniques. We can try out this process also. Trends in EV batteries. We should know about the capacity, the C rate, and that C rate only signifies either a charge or a discharge rate, which is equal to the capacity of a battery, and that is divided by an hour. So based on that equation, we get the current rating also. And we should know the cutoff voltage also, which is again the important aspect of a system. So prescribed lower limit voltage at which a battery discharge is considered complete. And you should know about a nominal voltage. So what is meant by a nominal voltage? Actually, when we talk about in the nameplate details, we have something called as a nominal voltage, because that is the voltage where it operates actually. So that is called as a nominal voltage. So that voltage of a fully charged cell when delivering rated current. I hope you understood. So nominal is that particular point where it actually operates. Means, for example, let us have a panel of 21 volts, but it will have a nominal of 18 only. It will give only 80. That is nominal voltage. Similarly, it is applied to battery also. Then moving to a state of charge. State of charge refers to the remaining capacity as a percentage of maximum available capacity, means whatever is remaining to maximum. The total maximum something is available, you have already used something. So state of charge depends upon the remaining one to the maximum one. So depth of discharge is also there. So DOD is the alternative method of indicating the battery SOC. So DOD is the percentage of battery. So I told you last slides, we'll calculate SOC with respect to DOD also. This is not equal to, this is with respect to. Similarly, DOD in percentage, that is equal to total 100% minus the state of charge, a simple equation. I hope this equation is very simple. Means you can see maximum minus the SOCs. Okay, all right, I'm able to write. Okay. Now, when you look at the depth of discharge, you will be able to identify the battery's charging status also. So this is one more alternative method to indicate. Now, trend in EV batteries. So I told you state of health is an important factor. Right now, the MTechs, they are having recruitment boon in this area. If you know about SOC, if you know about SOH, more in the electric vehicle sectors, you are given a job. So this is what SOH talk about. So parameter that reflects the present condition of battery. So what are the methods? What are this? See, now the research trend is SOC, SOH. But what do you do with the SOC and SOH? There are certain algorithms. That is what an electrical engineer is going to do now. So that is what I'm going to give an idea what we can do right now. So now when we talk about the SOH, it is the ratio of the actual capacity to the rated capacity. So we will talk about the cycle life also. Cycle life is also a major thing. That is the number of cycles that can be performed before the battery reaches the end of life. So this SOC, state of health, then depth of discharge, the end of life. All these parameters should be linked with the BMS system. So for end of life means mainly for the EV applications I'm talking here. The battery manufacturers define this end of life when one of the following conditions is reached. So what is the first condition? Maybe the 80% drop in the battery capacity, which is compared to the rated capacity, or the 80% drop in the battery maximum power compared to the rated power. When any one happens, we can define this end of life of a battery. And moving to the necessity of battery management systems to reduce cost associated with battery. Again, it is all known that includes the labor, maintenance, operation, and replacement cost also. To increase the lifetime of a battery, we need the proper thermal management and cell balancing. I told you this, I'm not going to concentrate. The proper thermal management or the cell balancing, I'm not going to talk about. So to ensure the energy of the battery is optimized to power the product, yes, to monitor and the control, we need the charging and discharging process of the battery. See, whatever we talk, we will talk only, anything we talk, it should fall under SOC, SOH. Whatever we talk about power electronics, finally it should end with SOC, SOH. Your battery is the ultimate controller there. See, like engine controller, it is a battery controller right now. So to provide the present status of the battery, see, that is what I told you, right? Completely, we should have the information about this. So battery voltage and current. See, in power electronics drive, we used to draw a diagram. I know that you all remember the diagram. See, we have a source, we have a converter, and we have a motor, and we have a load. Motor need not be a load anyway. And we have a controller. We have a controller, and sorry, this I'm giving to the source. It should not be a source. It should be the converter. So when I'm giving to a control, this is a controller. The output what we are sensing with that is with respect to V and I. I hope you remember the basic PED drive. This is a basic power electronic drive where you have the V and I from the output. You tap the output from the load. That is the input of the load. You tap the output from the input side. You tap the output parameters. They are the voltage and current. Output parameters of the motor, not the load. Output parameters of the motor. When I tap this V and I, this is directly related to speed and torque. So current, voltage, they are related to speed and torque. So that is what we are also talking here. This main battery management system, we talk about the voltage and current, that indirectly controls your speed and torque of your system. I told you, right? Initially I have drawn a speed and torque characteristics with the induction motor and an ICE internal combustion engine. I have drawn a diagram. So only 35%, 30 to 35% we get us a torque output for one particular speed in an ICE in an internal combustion engine, whereas you see 90% of torque improvement is there when using an induction motor. So means this V and I is directly related to your speed and torque, because battery is the only thing that is going to feed your motor completely, correct? So that battery voltage and current should play a major role. If your BMS, if this system is fed by V and I only, the output can be with respect to the, because you're driving a car, there you should need torque and speed. Next one is to enhance safety and protection of a battery unit, to analyze fault and provide alarm. That is a separate area. Now, functionalities and features of BMS. Now you can see the measurement of various battery parameters with respect to the cell voltages, temperature obviously will come into picture, current, insulation resistance, and so on. Now charging and discharging control is also a major aspect. Okay. So when we talk about the charging and discharging control, we talk about the primary goal, how to keep the battery in a safely operated zone. So the BMS must always protect the cell from any damage which is taking place while charging or discharging. And moreover, for lithium ion batteries, I'm talking about the lithium ion batteries, two-stage star charging method. Okay, two-stage charging method is there. See, when you take the literature, you can see different kind of charging, which is called as a level 1 stage 1 charging, stage 2 charging, stage 3 charging. It is going up to some 6-stage charges and all. But what is the stage charging? If you want to design a proper BMS, different stages play a major role, different stages. So this fast charging converters, this is what a major concern means. If it is a two-stage conversion means charging and absorption alone will be there. If it is a 3-stage, you have charging, absorption, and something called as maintenance charging, means floating charging. In the 3-stage, you can see the battery charging technology relies upon the computer chips. I'm talking about the embedded side. I'm talking about the microprocessor to recharge. So these all takes place. Now, this lithium ion battery, in the battery management system, you have the charging method techniques also. There we have the continuous current regulation mode, continuous voltage regulation mode. This determines the how your charge is being done, whether it is charging or discharging, whether you have 80% charged, or you can see in one stage charger or two stage chargers. So stage 2, let me take stage 2, whatever I have mentioned here. Now what is a stage 2? So once battery has reached some 80% of the state of charge, I'm talking about SOC. When it is reached 80%, charger will enter the absorption stage. What is this absorption stage? Practically, when we talk about absorption stage, only in this point of time, most chargers will maintain steady voltage level. Means after one period, you will have a steady voltage, but the amperage will be declining to a reduced value. If you're having a reduced amperage value, what will happen? The lower current which is going into the battery will safely charge up the remaining amount of the battery also. You got it? No, the point why we called as a two-stage charging. 80% it is charged. Now the remaining should be done with a slowly it should be done without overheating. That should be interfaced with your BMS controller. And stage also, the 3 stages also, we talk about something called as a 3-stage, which is a maintenance charger. I don't think so that those aspects are required for you right now, because that anyway, I'll tell you what is the maintenance charger also. It is otherwise called as a float charger. There, the time the battery reaches maximum 95%. So we started with 80, the first thing. Second, we slowly charge, and the last thing we move up to 95% of charging. So charging here in the 3rd stage will continue till 100% capacity is reached. Okay, so here the charge will continue to monitor the battery, and what will happen is when we apply some charge, also we can detect whether there is a loss in the battery also. We can decide all these things in the charging methods. Moving to the functionality again, we talk about the thermal management. We know that battery temperature, yes, I told you should do it without overheating. Then protection is also there. Over voltage protection, over voltage, under voltage protection, short circuit protection, thermal protection, isolation measurement, high voltage interlocks, all these come into picture. And SOC and SOH are determinants. There are different techniques. I'll tell you what are the techniques later. And this cell balancing is again method of compensating weaker cells by equalizing the charge. I'm not going to going into depth into it. So logbook function, again, whatever data we have, we are making it into the memory of the system. What is the data? Again, charge, discharge time, battery parameters, and things like that. Now I'm moving into the functionalities and features of the battery management system. And this is your centralized BMS. I'm talking about the centralized BMs. The battery interface here, the centralized thing will consist of single installation point. It is single. Everything is here: balancing, temperature control, charge system, the hybrid vehicle safety control, the relay driver, communication module, the safety indication. Everything is completely in one such module. But what is the major disadvantage is the complex wiring, again, which can be taken care. Moving into the next category is your distributed and modular topology. Here in this modular topology, you can find different this complex controller units also there. And here your CAN bus will come into picture. I'm not going to detail about it. And here each cell is given to a cooling system. I told you, right? I told you Tesla is an example, right? There we can see we can see the cooling system. Means let me draw. I'll try to draw. I'm very poor in drawing, but anyway, let me tell you, give you a small example of what it is. I should need a space to draw. Let me, okay, somewhere here. So you can see the architecture. You have seen the previous architectures. So here, let me say, something like this. Let it be a car. Hopefully looks like a car. Here we have a battery. Okay, here we have a battery. Now, let me take, I'm not talking about BLDC and all, I'm just talking induction motor for us to understand easily. Here, this is completely battery bank. This is induction motor. And here we have an inverter. This is power electronics here. Now, this battery management system inverter, this is the heart of the system. So here you have a conversion, which is again fed to the induction motor. Now, I'm telling this functionality, the distributed topology here. I'm telling you which area what is being done. This battery, this is the battery, whatever I'm shading here. In this battery area, we can see batteries being placed, and I told you the cooling system, right? Here, because they're all attached, they're all detachable. We can take and replace it. There you have a cooling system, which is again, we can have an outlet here, the dotted line here. Now, this place, you can see the controller here. Each cell is being controlled with the cooling system. Even those things, the voltage, temperature are also there, and which is there given to the BMS display. I think you can imagine now whatever I have drawn, what is being done, what this diagram is all about. I hope you can imagine whatever I told you right now. So this is what is being done in the modular or distributed topology. And moving into the estimation of SOC and SOH. Now here, this is the place where we electrical engineers need to concentrate. Okay, we know that. For so long, I've been talking more than an hour. I was talking about SOC and SOH. So why SOC? You might have understood. That is the pulse of the battery. The pulse, this charge is the pulse of a battery. So you require SOC. So you understood. Why requirement of to estimation of charge? Flow diagram to estimation of charge, or something called as Coulomb counting. What is it? And so what is this SOC and open circuit voltage for lithium ion batteries? What is this discrete domain? Why SOH? What is this SOH algorithm? We talk about Kalman filtering even in this battery modeling, what it is, and parameter estimation in Kalman filters. I'm not going to depth of Kalman filters. It is something that I don't want to make you bored. I just want to talk about the power electronics concepts, but just the gist of the available options we are having. These are all available options. See, I will tell you the idea alone, how you have to model this, so that anybody can go for any algorithm and modeling. So this is the summary of estimation of SOC and SOH. And going into the SOC, I already told this, we have seen in the previous slide itself. So the remaining to the maximum charge, we talk about the SOC. And again, the state of health is an indicator for the health of the battery. We all know that. That is with the nominal capacity, means the actual operating capacity to the last one, with to the nominal capacity, means the nominal to the lost capacity difference to the nominal capacity. So this is called as the state of health. Then moving, why SOC? Let me skip. These are all theoretic aspects. Let me go into the power electronics. So these are all required performance. Yes, we need performance only. That is why we are going to think. Let me go here. Wait. So let me talk about the estimate the charge. See, I'm going to show a diagram. We need to follow certain concepts to design an algorithm or to design the idea behind it. Okay. So EVs need to know two battery quantities every time. I'm talking about everyone. This is the research point of view. First one is we should know how much energy is available in the battery pack. Okay. Second one, you must know how much power are available in the immediate future. So you need to know or estimate. I'm giving about the definition. In Tamil, we call it as the pair karanam. Pair karanam means the state of charge. Why it is coming like that? Why we are giving the name estimation of state of charge? So when we talk about in Tamil, we talk about pair karanam. So estimation of state of charge means how much energy is available. So these two data is required usually. So how much energy is available in the battery pack, that is what we need to estimate. So finally, estimate of energy is the most important of EV. But how can we estimate? That is the idea, right? See, we all say that we have to estimate energy, but how do we estimate that energy? So estimation of power that can be computed by cell state of charges and capacity. So to compute power, we must know all cell state of charges and resistances also. So you understood. We need charge as well as the resistance. So without this, we cannot compute the energy or compute the power. So if you want to compute power, we need to know the charges and the resistance. If you need to compute energy, we need to know the charges and the capacities also. So that is what it is given here. So this is the generalized flow diagram. This is something like a diagram similar to a flow chart. Okay. Input voltage, current, temperature. These are the model based estimators. And the output of this is the charge, state of health, and resistance. We calculate it. Output, we get energy and power. I hope you are clear. Again, I'm repeating. This is something like a flow chart where the estimators will have input as voltage, current, or the temperature, and output from the estimator will be the total charge or state of charge or the resistances. And from pack calculations, we can determine the output as energy and power. These are the output we require. This is the output. So this is what we need. This is the output we require. So based on that, we are giving some input. But we can see they're all non-linear parameters. See, again, I don't want to talk about control system and make you get bored. And we talk about, again, we cannot violate control system here. There are non-linear equations. We wanted to make, see, these non-linear parameters, basic architectures, all these non-linear, we are trying to find some linear thing with respect to that. Without linearity, without some linear aspects, without determining the linear aspects, we cannot drive a vehicle. You agree, no? See, We don't know what is, if you are driving a car, we need to predict what will happen. If you put a brake, what should happen? If you release the clutch, what should happen? If you accelerate, what should happen? That is all predetermined. But again, these determined qualities arrive from a non-linear constraints only, right? There are different factors. If your internal combustion engine does not work properly, your flywheel or your thing should come into picture, should support you to make a rotational motion. So they are all linear. They are not linear parameters. They are all non-linear parameters actually. But finally, the output power energy you're getting obtained becomes a linear parameter. So to determine all these things only, we are determining a flow chart. So flow diagrams to estimate the state of charge is required. So I'm shifting. I'm not going to here. Let me tell you what is meant by a Coulomb counting. So I showed you some diagram, and immediately I'm coming to Coulomb counting. What is it? What is it actually means? If I wanted to design a flow chart, I need to know about the Coulomb counting. So what is this Coulomb counting? If we talk about the discharging rate of flow of current, means this is actually a technique to track SOC. Technique to track SOC. And it works by integrating active flow of current. Okay, and that current is only discharge current. So over time we will derive it, and all the sum we will take and we will calculate. That is the current entering and leaving the battery pack. This is called as Coulomb counting. This detail we require. So it means that previous one with respect to the present one, means this is the bilinear transformation. We talk about mathematics. Trapezoidal method is a method where one area, so one area you will divide into trapezoids, and that area you will find the values. That is bilinear transformation actually. Now here this is something related to Coulomb counting also. So this numerical integration means over a period of time. See, I'm writing a mathematical equation. We need not get worried looking at a mathematical equation. This is just a logic. See, it works by, I'm again overwriting, integrating active flow of current. See, I'm writing an equation here. Integrating a current. Again, I'm telling which varies from period of time. Okay, with respect to your sum which is entering and leaving the battery pack, which determines the capacity of the battery. This is how we determine the equations. And moving to the state of charge and the open circuit voltages for lithium ion batteries, here we can see this is used for correcting the state of charge. By measuring the open circuit voltage, we can determine the state of charge. That is what we have here. And for practical applications, this curve is used using a table or some curve fitting algorithms. But this is required. This open circuit voltage is required. So only OCV versus SOC for lithium ion batteries is essential. Now, discrete domain. What is this discrete domain? Suddenly I'm moving to some equations. Okay, what is this equation? Why I'm moving into an equation? So without this modeling, we cannot do it. That is it. We should be good enough to model an equation. Now, I don't want to model and confuse you with all the topologies. I'm just telling you what this is all about. Something I'm determining here. I'm moving here also. I'm not talking about the, wait, I'm here. This diagram, you can see this diagram. Here you can see, for example, let this be a state of charge. We have a state of charge and we need to know the state of health also. And I'm writing in the function. See, logic is any equation we write, we should model it. This model should give the output with respect to the state of charge. Okay, we electrical engineers should be capable of transforming the equations to a model. That is what we are doing doing this in the discrete domain. Okay, means we are replacing it. How? See, you can see, for example I'm writing here. So this is some state of charge with respect to some function. Okay, some function we are writing. Now the state of charge we can have with respect to some function is discontinued here. SOC minus here. Again, it is we can write some equations. Okay, again, this is the function of current, actually some function of current. I'm not writing the correct equation, I'm telling you how we will write write some equation. So it is with respect to some charges, means this is the previous one, or it will take the sample, it will take the equations, it will correct by itself, it is used the corrected initial corrector and initial computation, and finally we need to know this SOC. Means ultimately BMS require SOC. So there are methods to calculate SOC. That is what we are trying to do now. So we have drawn a flow chart. No, I told the flow chart we need VIT. Finally, we need battery energy and power. So in order to get this battery energy and power, we require BMS. That BMS only we are doing here. That BMS, SOC, SOH only we are determining. So there are some methods to determine this SOC and SOH in electrical engineering. That is what we are doing it in either in Coulomb counting or in ECC algorithm. We are doing this only. Now, moving, why SOH? Yes, we require for the prolonged battery life. I'm skipping this and say whatever we have explained regarding the state of charge and Coulomb counting I have placed here, and moving to the Kalman filtering. Some of them might have done their research in Kalman filtering also. So see, we need something, as I've told you, I'm taking SOC itself. Why I'm not able to write now? Wait. Okay. In SOC, I'm just taking an example of a first order integration or first order differential equation. Okay, first order differential equation. This is a function of voltage, current, and even this can be SOC itself. And we need SOH also. First order equation is a function of, again, voltage, current, SOC, and SOH. Okay, we know. I'm trying to explain you this equation. These are all non-linear parameters. And finally, for example, this should come to 0, this value, or else we can have a function of fx, means the first order equation. If it is x, f of x will be something, x square by 2 something, or t square. Okay. Now, for example, if this is a non-linear function, we should make this a linear function. We should make this as a linear function. So that is why we go for some different Kalman filtering techniques and other techniques also. Ultimately, objective should be, ultimately the objective should be, basic idea should be, in real time, the errors between the measured and estimated output. So that is corrected. Error is corrected. We talk about different algorithms, but the objective is the error is corrected. This is the important idea. So corrected model then estimates the accurate states of the system. Means, for example, you are getting an error, you are correcting the model, that determines that output is fed again to the system of the flow chart. That, there is no proper method to estimate a parameter here in the EV. So we are going for such algorithms to determine the state of charge and state of health. So that is what we are doing it. Prediction and correction. No, I'm not going to depth with the Kalman filter. Modeling equations with respect to the voltage, current, and SOCs and all we have placed here. Again, we are going with the equivalent model, the Thevenin second order model. There I have told you first order model as an example. Here we have given Thevenin second order model. I'm not going to depth of it because I'm moving into the power electronics aspects. Okay, I'm not going here. Now we'll go with the See, you can see here. Now we tell that in certain models, the inverter is the heart of the system. Now moving into the EV battery charges, which is on board or off board. See, this gives you a complete idea. So this is the guide. This is the guide where what will happen. There are two kinds of charges. One is the off board, one is the on board, and the down part is completely battery. That means the battery which is connected to your system. This is your battery. Now we are going to now we are talking about the EV and battery management, right? So we should know what is happening here. This is the power grid. In case in future this is the grid supply. We will have this tappings everywhere. This is car. This side is car. This side is this offboard is from the grid supply. Here you have different topologies. You can see the AC to DC converter is there. Again, DC directly from AC to DC. Again, DC to DC is there, which is again there in the DC, which is there in your car here. Here from power grid, you are taking AC to DC. Then again in car, you have a DC to DC converter. There you are feeding a battery. Next combination is also there. AC DC is there, and again DC to DC converter is there. Here directly a plug will be only available, which you can just plug it to the battery. That required amount of battery, it will charge easily. So these are the things. You will wonder why there is a blue color, red color. Now we can have some red as an IGBT or thyristor based, which is a blue color. And we know power electronics. We know if you use an IGBT, the bidirectional flow is possible with the freewheeling diode. Correct. Bidirectional flow is possible means either the grid to a vehicle or vehicle to grid. The bidirectionality is possible there. So that again here you can see in AC to DC converter, again DC to DC, which is again being fed. Here only one converter AC to DC is there, and these are all whatever is there available in the car set. Here you can see battery. Here this is available. Some suppliers give separately a controller unit or charging unit. You can take it. That is handy actually. You can just connect it directly. You have a separate charge controller. There you can just plug into the EB supply. Then you can use this controller, which is fed again. Just one wire will be there, which is connected to the battery of your car. This is very important topology. This is where you can go for research in case. You can do wonders in this slide. See, you can do n number of research in this area. There are scopes just like anything. You see, you cannot believe the scope of the research in this area. And you can see the beauty of the power electronics here. You can see, you can design a converter here. You can design how a converter will behave. Various topologies you can see. I told you, in the first slide when I started, I told you what is that research that is needed. So various converter topology. That is what is required in this area. And moreover, we can see one important aspect: battery modeling with respect and battery modeling, safety and state of charge, and also. We should be thinking of, can we replace the charged battery into the electric vehicles and charge the discharged one at leisure time? That is also we should talk about. So all these things here, this converter will play. And design of converters, various converters for fast charging. This is trending actually in power electronics right now. So if you talk about these converters, we have with respect to onboard battery charges and offboard. I told you, onboard there in onboard, you have seen here this onboard. I'm talking about this onboard. If you see the onboard here, it's a simple conversion. You have an AC to DC conversion. Here the front end stage is a simple diode AC to DC converter. It's a diode rectifier and followed by a boost type DC to converter. You can see this AC to DC, again DC to DC. And this topology has the main advantage of using only one switching device. Still guaranteeing the operation with sinusoidal current and unity power factor. All these things, which is what is required at the output side, load side. But that is what I'm telling you. Like this topology, you may decide n number of topologies to bring the best output. That is the research you are having in your hand. You can decide any converter what you want. Then onboard battery chargers, which is continued, and here you can see the future perspective of electric mobility as support for the smart grid. A bidirectional operation is essential, in which 4-quadrant AC to DC converter is used. See, whatever we studied in book, we are implementing. That is bidirectional full bridge converter. It is simple, a bidirectional bridge. I already told you, we use an IGBTs here for the bidirectional flow along with the freewheeling diodes. So this converter will allow the bidirectional operation. Means what? grid to vehicle, vehicle to grid, without neglecting the sinusoidal current and the unitary power factor. One more topology is there. You can see again, it is an onboard. This is most common bidirectional interleaved full bridged, which is an AC to DC topology. I'm just showing few converters, which is converted again. This is a three phase. If you wanted to charge the battery very fastly, you require a three phase. The three phase which charges the battery, which is the DC load, the DC. Now moving into the other configurations also, you can see this is also one of battery charger. See, the main objective why I'm going for a different topology here is to reduce maximum voltage applied to each semiconductor, as well as to reduce the requirement of passive filters. Means I'm going to use a T-shape setup. Here, if I use the shape, this problem created by these inductors and capacitors can be completely eliminated. So the choice lies in the multi-level topologies. I'm talking about the multi-level topologies. So moving into the off-board, I told you off-board, which is directly you take from the grid supply, you feed it to the converter setup, then you charge it. So regarding off-board electric vehicles, or for the onboard, whatever it is, there are several options. That is what I'm telling. There are several different options. All these, what we require is the fast charging techniques. Again, this is what we discussed. All the institutes, we focus on the fast charging, battery setup and converters. No, this is going to be the trend in future. This is what I'm telling the area. You can work on it. Moving into the off-board battery chargers, same thing. You can see same three phase, which is there. Only see, look every time when I'm showing you a semi converter or a full converter. When you talk about a power electronics, we get the output as per the required thing. Same here is our intention should be bidirectional flow. That's it. Grid to vehicle or vehicle to grid. It should be done by a converter. So there are different converter topologies. Here, this is one such topology where we use a three-phase topology, which is guaranteeing the both side flow. That's it. So this topology is made up of three legs. You can see made of three legs. So the DC link is divided here, where the midpoint is connected to the power grid neutral. That midpoint itself is connected to the power grid neutral here. So moving into the next off-board battery charges, same here. Here also you can see the desired output is obtained here. But here you can see a phase shift thing. See, there are different converters where it operates with the phase shift with the two carriers at a phase shift of 180 degree. This is being done here. And here also, this is very important since it can also be useful to reduce the need for passive filters and in coupling to the power grid. So there are, see, that is what I'm telling you. There are different kinds of power electronic converters that can be used. And auxiliary battering, this is something like what we can have it in our home, this auxiliary battery system. You charge with the smart grid system. This is for the battery in the car. And again, you can have a full bridge isolated DC to DC converter. It means an auxiliary battery. When one is not available, we have something in hand to auxiliarily support a system. That is this auxiliary battery setup. So this EV must be equipped with a charging system for the auxiliary battery also. In the same way as a conventional vehicle, the electronic loads of EV must also be powered by an auxiliary battery. And that battery is something lesser value, means a low power battery. So driving should be always with the comfort, a feeling of safety, and driving support should be proper, which is completely available in the BMS interface. Whatever you're looking, the battery management system, the controller, the display should give you all the values. Now, battery integration challenges are there naturally. We have, I think we might have read in news also, solar powered EV is also available where the battery is integrated. But there are challenges with it, and integration of the solar storage system has many questions which is open, because transferring from lab to real world applications definitely will have its own, but over a period of time, they will have its own market in the in the globe, around the globe. And also the high storage device temperatures, the aging factors have definitely the impacts on the efficiency and moreover the reliability of the system too. And thermal management that is related to the batteries. And let me show you few micro inverter. Here it is a 3-port micro inverter. You can see there are 3 ports. So 1 port you give the input, 2 ports you take the output. So battery technologies with the power electronics here. So this is what it has been done. A small example of it. If you see an electrical bike, a small bike, you can see the charge controller. Only the small MOSFETs you can see. The power MOSFETs will be used there in the inverter level type. If you see that, it's a small board only. You can easily replace it. It's completely electrical. Then moving into the battery technologies, here you can see you have a panel, you have a battery, which is 2nd port, and 3rd port is a grid here. From this panel to battery, you can charge. Then battery to grid, you can supply. Then the grid to battery, you can supply. And this panel to grid also, you can supply. So multiple points is possible. Multiple topology, one single topology, multiple actions are possible. So these are the beauty of power electronics actually. Then battery technology. So this is something like a resonant converter, which is LLC micro inverter. Here you can see a battery which boosts the output here, where you want a very high voltage at the output here. It is behaving as a proposed topology where the output DC to DC converter will have a higher value, means the input to take the output with a higher value. Here is a PV, you know, it's a DC. Then you can have an output here. It is a dual input LLC. You have inductors, capacitors in the micro inverter. This is a micro inverter prototype. This is a proposed DC to DC converter, which is again isolated, and that interfaces one PV panel also and a battery energy storage. See, interfaces. That is also possible right now. So they have different power flow scenarios. So let me conclude that the weak link in EV batteries is like it is not yet still matured. The research and development in this BMS is needed to satisfy the standards of the vehicles. Naturally, the battery PV systems for EV chargers can be developed in future. And there are challenges in BMS also, like we can find an accurate and practical algorithms. I have told you, right? There are different algorithms and discrete algorithms. You can, the trapezoidal method, discrete transformation, Kalman filter, different modeling can be done, and those nonlinear parameters can be sorted out. So those are the challenges which is still available in BMS. And we need to develop standards also, like we have an engine control standards. We need to have this BMS standards, which is very, very important. Developing standards. So standardized definitions of SOH can be varied. So coming up with high efficiency, cost effective parameters. Balancing method should also be done. When a cell count is very large, how it can be balanced, that is also an area. So naturally, developing accurate battery models is again a challenge in this area. So these can be sorted out, and I've given you the future of the research. You can see the fast charging batteries, which converter will help you in fast charging batteries. This is a research area with respect to power electronics. So these are the references. You can view that. And some references I have not mentioned here also. There are the recent references which happened in past 1 week or 1 month. All those references are I've not listed here actually. These are the old references. And yes, I should thank everybody. So thank you all for giving me an opportunity. Especially I would like to thank the HOD of the department for giving me a wonderful opportunity to share about the BMS and power electronic aspects with respect to this. And really now I will tell you the future is electric vehicles. Definitely the market will be dominated very soon. If we have just the charging stations, I have showed you know in a slide, from the grid, off-board, on-board chargers, if it is entering into the market, that's it. We can have it easily. And also we need competitors. There are only few people who do this. We need competitors. That is what everybody can try this out. It's not that very difficult. You need the logic, you need to do it, that's it. So thank you all.
Participants, if you have any queries, kindly interact. Participants, if you have any queries, so kindly interact.
Madam, I'm Mr. Godse.
Yeah.
Uh, to what extent we can measure state of charge of the battery correctly?
What's up? I don't get your question.
What is the accuracy in the measurement of state of charge of battery?
See, accuracy is still under the research only. See, we cannot actually predict the actual accuracy of state of charge. So that is why we are dividing into the level of charges. I hope you got my point. Actually, the accuracy. What should be the percentage of your battery charge?
What is the percentage of? Presently, we are getting the idea from the fuel gauge.
Okay.
What is the level of petrol and or diesel in the tank?
Okay.
In the similar manner, to what extent there is the accuracy in the measurement of state of charge of battery?
See, we cannot predict the actual accuracy of the state of charges, because we say that usually we have something with respect to 80% of a level, something which is 80%. I'm talking about a percentage here. Okay. So yeah. So if we talk about 80%, so that is the first level of your battery which can charge actually. And after that, your battery will slowly enter into a slow phase of charging only. So with one benchmark, we can say that it is entering in a minimum of 80%, and after that it will be slow only. But definitely any battery should be charged with 100%. See, it is similar to like we are fueling the tank, right? How much ever we fill the petrol, that is a fixed tank. You can have some 25 liters or 27 liters there. Here it is like charging and discharging here. So that should be with respect to the charging and discharging levels, which is interfaced with the controller. You got it right?
No, madam, my question is different. Madam, battery has a degradation effect. With age, we cannot have the same charging capacity. Okay. Suppose a car is purchased in the year 2020. Okay. And thereafter, after 1 year, 2 years, even though it shows fully charged, okay. So driving may not be, or the same mileage we cannot have from the same charging.
Okay.
One charging, suppose car is running for 400 kilometers.
Okay.
After 1 year, for the same charging, even though full charging battery is showing, we cannot have the 400 kilometer running.
Yeah, definitely it won't happen, sir, because the current which is being drawn, that either increases or decreases the battery life. That is right. So we can have a minimum value of like the percentage of charge only. So right now we cannot fix it right now. Still, it is under research, sir. So we cannot actually have like one particular value for this, because each manufacturers, they follow it in a different value. So that is the place where we can opt for in the future research.
Okay, thank you. Madam, please share your content, email ID.
The content, okay.
Any more questions from participants? So I hope there is no further queries. So on behalf of management of KPR Institute of Engineering and Technology and organizing team on my own behalf, we are very much thankful to our today's resource person, Dr. Oral Josephine ma'am from NIT Trichy, who shared her wide research experience about necessity of BMS system, of board charger, battery technology, then importance of power electronics for EV and battery management system, and she has pointed out the challenges in a battery management system too. So really, this session is wonderful, ma'am. So thank you so much for sharing your wide experience in this right occasion. So thank you once again.
Thank you, sir. Thank you so much for giving me an opportunity to talk about the future of EV.
Okay, thank you. I thank all the participants for your valuable participation. So happy learning. So next session will be at 2 p.m. Thank you so much.
Thank you.
Thank you, ma'am. Thank you.